Hello and welcome. My name is Luke and welcome to this video in this Pytorch tutorial learning series. In this video, we're going to look at transfer learning. So in the previous video, we looked at how we can construct our own deep networks using residual and skip connections, and we saw the benefits of those. I also hinted at the end of the video that Pytorch also has implementations of not only the individual layers, but whole model architectures. And so what we're going to look at in this video is look at implementing some classifiers using the pre-built Pytorch implementations of some of the classifiers. So the model architectures that we're looking at, or that Pytorch has implemented for classification, you can see we've got some ResNets and various architectures here, and these are based off of a whole bunch of research papers. So ResNet here introduced sort of the residual connections, and we did residual connections, but the architectures in here are specifically copying the ones in those papers. Same with the other architectures. Not only does Pytorch have the architectures pre-built for us, but they also have pre-trained models or pre-trained parameters for those models. And so we're going to look at a technique called transfer learning, where instead of training from scratch the random initialization of those parameters, we're going to use these pre-trained parameters as a starting point, and we're going to see how we can get a boost in performance, particularly in the case where we don't have a lot of training data. So you can see I've written here, there might be the case where you have complicated data, so large images that might necessitate a large model, but with a large model you need a lot of data. So what happens when you have large images but not many of them, and so you need a large model? Well, the first thing we're going to look at, and we're going to look at different techniques in subsequent sections, but in this video we're going to look at transfer learning. See how much of a boost in performance we can get simply by starting at these pre-trained parameters. So the dataset we're going to be using in this this section, this notebook, is the STL10 dataset. So the STL10 dataset, I've kind of cut this off a bit here. If I move this over, the STL10 dataset is a dataset of images, but it only has 500 training and 800 test per class. There's 10 classes, so it's 5,000 training and 8,000 test images. And also, if you note, it has about 100,000 unlabeled images. We're not going to do anything with those in this section, but in the next section, we're going to look at how we can utilize these as well. But in any case, for this notebook, we only have 5,000 training and 8,000 test images. And so what we're going to do initially is we're going to train on that data set without any pre-trained parameters, and then we're going to use the pre-trained parameters from Pytorch, download those, and we're going to see how much of a boost in performance we can get. So we're going to train this network a few times with different sort of permutations, and we're going to look at another technique called weight freezing. So this is also transfer learning, but the idea behind weight freezing is that if we have a large neural network model that has been pre-trained, maybe we don't need to train the entire neural network again. Maybe we can only train parts of the network. So the ResNet 18 architecture, which is what we're going to look at today, is an 18-layer ResNet neural network, CNN, and it consists of basically a whole bunch of convolutional layers, similar to our ResNet we saw in the previous video, and it's going to have a final fully connected layer that will then output the class activations. All of these pre-trained models in the classifier for Pytorch's classifier pre-trained weights have been trained on the ImageNet dataset. The ImageNet dataset is a huge dataset, millions of images, and 1,000 classes. So millions of images broken up into 1,000 classes. The STL10 dataset is a subset of ImageNet, so it's a smaller portion of ImageNet, but only 10 classes, right? But your dataset might be slightly different or have a different subset. It might not be similar to ImageNet. And in that case, if you don't have 1,000 classes, we need to modify the output of our model. If you have less than 1,000 classes, potentially you could use that output layer with 1,000 outputs the same. But what we're going to show you here is how you can simply swap the final fully connected layer for a new one. It'll be randomly initialized, but we'll see how we can do that and then train the model from there. So those convolutional layers will stay the same, but we'll randomly initialize or reinitialize that final fully connected layer. So we'll look at weight freezing again. So weight freezing is where we freeze all those convolutional layers and only train the last linear layer. And we'll also see how we can train the entire model as well. And we'll just see the difference in performance between those and what's it like. Okay, so again, the training test validation split very similar to before. STL10 dataset's a little bit different how you initialize it. You define the split training or test. Again, there's no validation set, so we're going to create one randomly as well. Okay, so let's look at how we can use one of these Pytorch pre-built models. It's very simple. The models all exist in this, where is it? Pytorch vision.models. So we're going to import that as models. And there are a number of different ways you can initialize this. The simplest way is to just do models.the model name. So we can have a look at all the models here. So AlexNet, ConvNet, there might be different versions. So for our ResNets, we don't just have ResNet 18 with 18 layers. We have 34, 50, 101, 1, 2, 5 as well. So very deep models. So we would do ResNet 18 for 18, ResNet 34 for 34. If you're using an older version of Pytorch or older than 0.12, this is the way that we would set or tell Pytorch whether or not we want to use the default pre-trained weights. Newer versions of Pytorch, they've changed the API because they want to introduce multiple sets of pre-trained weights per model. And so you might have ResNet 18, but you want to use a different set of pre-trained weights. So they've changed how you can do that. You can still use this method. It's depreciated. They'll give you a warning if you try. The newer method is something like this. So we set weights to some string. You can say this is ImageNet 1K 1000 classes version 1. Some of the ResNet models have a version 2, which is a slightly different training regime that they've implemented. It's still ImageNet 1K 1000 classes, but they've updated their training regime to get a bit better performance. ResNet 18 only has a V1 though. I think you have to go to ResNet 50 before you get to V2. You can also have a look in the pre-trained weights, the actual accuracies. So what we've got here is the top 1 accuracy and top 5. Top 1 accuracy is looking at the accuracy for the activation function that's the largest. So you're looking at the top prediction for a particular image and comparing that against the ground truth. That's top 1. Top 5 accuracy is saying, is the ground truth in the top 5 highest activation functions? So is it somewhere in its top 5? Which is a common metric to use because for just classification where you're asking your model for a single class output, it can be a bit ambiguous. Some of the images can be a bit ambiguous. There might be a cat and a dog in a certain image. When you have data sets of millions of images, it can be kind of hard to filter out things like that. But in the real world, there might be a dog in front of a car. Is that a picture of a dog or a car? So this top 5 is just saying, as long as the true class is in the top 5, then we say it got it correct. But I just want to show you as well, you can see for our ResNet 50, ImageNet weights V1 gets about 92 top 5, but the V2 has a 90. So 92 versus 95. Right, exact same model, different training regime. And in that case, you would specify V2. But you can see a lot of different model architectures and a lot of different parameters, sets of parameters. But we're just going to use ResNet 18 with the V1. You can also, if you want to go through this documentation, you can look at the different APIs that they have for actually initializing it. If you don't know what model parameter set to use, you can just set it as default. And for ResNet 18, that's just this model here. It's usually the first one. Oop. Oh, I'm using a different environment, sorry. I've got an older version of Pytorch here, just for people following along. So if you've got the newer version, you can run this one instead. But that's as simple as it gets, really. If you want to use the pre-trained weights, you just set this to true. But we're going to start off with the untrained parameters. We're also not going to freeze the model parameters yet. We're going to train this purely with the whole network unfrozen and see what accuracy we can get. So let me just print out this ResNet architecture. You can see that the architecture is made up of, similar to what we saw in the previous video, made up of multiple blocks. They've got multiple blocks within a single sequential block. So this sequential block is 2 sub-blocks. This sequential block is just 1 or maybe 2. The sequential block here is just 2 again. So you can see how they've also built the network up from these smaller sub-blocks and stacked them in the sequential block or multiple sequential blocks. And you can see we've got an output linear layer here, 512 features in and 1,000, 1 per class out. We also have an adaptive average pooling layer here. This adaptive average pooling layer, I won't go into too much detail on this, but we saw max pooling as a way of downsampling. Average pooling is similar to max pooling, except instead of taking the max value, we take the average over that window. And adaptive average pooling is just a dynamic way of creating an average pooling layer where we don't specify the size of the window. We specify the size of the feature map that we want as an output, and then on the fly, that adaptive average pooling layer will calculate the size that that window needs to be so that the output is a specific size of the window and the stride, so that that output is what we want it to be. We include this, or Pytorch has included this here, so that we can use any sort of image size for this particular model, right? Because if we put a very large image in, after all these convolutional layers, we're going to get a certain size feature map, and this linear layer is expecting 512 features in. But if we put a smaller image in, we're going to get less features, put a larger image, more features. So this adaptive average pooling is making sure at this point, right before the linear layer, we're going to get a 1-by-1 feature map by 512 features, right? Output of the final basic block is 512 channels. So it's going to be 512 by 1-by-1, irregardless of what sized image goes in. Hopefully that's clear. But as I said, we don't have 1,000 classes. We have 10. You could leave it as is, but it's not best practice. So what we're going to do is we're going to replace that final linear layer with our own. So we're just going to quickly get these 512 features here. If we just specify ResNet FC, which is the final layer, and then linear layers have a parameter called inFeatures, which is the number of input features. And we're just going to use that to define our input features and then our 10 classes out, making sure we're putting this onto the device as well. Okay, we're going to be using the same model trainer class from the previous video, but we'll go into a bit more of the details or the updates to this model trainer from previous sections. But for now, we're just going to pass our ResNet model as the model, and as well as all the other parameters here, as well as this start checkpoint or start from checkpoint, which we'll go into in a moment. But similar to before, we also pass the datasets, and we'll have a look at some of the images. So these images for STL10 are 96 by 96, so quite a lot larger than the images from Cypher 10, which was 32 by 32, 3 times larger. So 3 times larger, it's 9 times as many parameters, or 9 times as many pixels, so a much larger input. You can also see that our model has 11 million parameters, which again is quite a lot larger than the models we're used to. At this point, you will probably start to need a GPU in order to train these models. If you don't have one, that's okay. There are some free services I'll just quickly shout out, like Google Colab. If you have any other ones, you can leave them in the description. But Google Colab is good for running Jupyter notebooks. You get a really relatively low-grade GPU, but that should be enough for running these notebooks. So have a look into Google Colab if you are starting to, or you will start to notice a big slowdown if you're trying to run these larger models on a CPU. Okay. So let's go into our training loop, very similar to before. It's almost identical to before, but we'll go into a bit more detail into this checkpointing here. So I didn't really cover this in the last video, but what we're doing is we're going to save the parameters of our model and the optimizer, as well as some other parameters, so that we can reload them later on. So we can save our model and then maybe reload it to use it for whatever application we have, or so we can reload it so we can continue training on. Right, so what we're doing here is we're comparing the best validation accuracy for the model, which we initialize to 0, as we'll see in a second, and we're comparing it against the current validation accuracy. So we've trained, we could have training accuracy, validation accuracy, and then we're saying, is this validation accuracy better than the current best validation accuracy? If so, then we save the checkpoint. We only save if the current model is better than the old model. We do this so that we don't save our model if it starts to overfit. So when our model starts to overfit, you'll notice the validation accuracy goes up, and then it may plateau or it might start going down. So the training accuracy will continue to go up, but the validation accuracy might start to drop. And so we're going to not save our model if it has a worse performance than before. Okay, so let's look at how our checkpointing works in our model. So our save checkpoint function here is relatively straightforward. You can see we're setting the best validation class parameter to the current validation accuracy because that's the best one. And then we're using the torch save function, and we're passing that a dictionary that we'll get to in a second, and also the save path. This save path is defined in the train model init function, and that is the save directory plus the model name that we define at the very start. ResNet18 underscore STL10. Okay. So this dictionary that we pass it is what we're going to be saving. The two main components I'm going to focus on is the model state dictionary and the optimizer state dictionary. So all of the parameters of our model and all the learnable parameters and any other parameters such as batch norms, running mean, running variance that it saves, or any other layer types that save some sort of values will be contained in this state dictionary, and we're going to save that. Same with the optimizer state dictionary. The optimizer has things like the learning rate, or if it's a more advanced optimizer, it might have the momentum components, the variance components of the gradients that it also needs to save, so that we're not starting from a completely random set of momentum or completely zero set of momentum and variance. So we want to save the optimizer state dictionary as well. And we're also saving the best validation accuracy and our training and loss and accuracy loggers that we initialize to just some lists here. So loading the checkpoint, we can also load the checkpoint from save, which is very important. You can see the last thing we do in our initialization function is check if that start from checkpoint flag is set true. If so, it'll call the load checkpoint function. This load checkpoint function checks if this checkpoint actually exists. If not, it'll raise an error telling you it doesn't exist. If it does exist, then it will use torch.load to load that save path into the checkpoint. So this is a dictionary, our dictionary that we saved, and then we're just going to unpack it. To load the state dictionary back into our model, we simply call load state dictionary and pass it the model state dictionary. Same with our optimizer, and we're just going to unpack those other values as well. You'll notice that if start from checkpoint is false, it'll quickly check whether or not that path actually exists. If it does exist, it'll raise an error and say, hey, this checkpoint actually exists, but you want to start from scratch. Do you want to do that? This is just to prevent you from overriding your previous save. So it's making you or forcing you to manually delete it or change the actual model name that you've created. I can ensure you that I've seen many times students accidentally overwrite their save models that they've spent hours potentially training. So I give them this little extra bit of code to make sure that the code is checking and preventing you from oversaving your old models. So hopefully that makes sense. That's just a quick look into checkpointing models. Very big thing as well that you'll probably want to do with your models. So with that, we'll start our first training run. So as I said, we're training the full ResNet model without pre-trained weights. Remember, we've only got 5,000 training images. This is going to take a little bit of time, so we'll get back when it's done. All right, so we've only trained it for a very quick amount of time, only 10 epochs, but you can see in that time we had a highest validation accuracy of 52%, I haven't printed it out, but we can have a look at the last training accuracy, 100%. So we've got 100% training accuracy, but only 52% validation accuracy. You can see our model has really overfit to our training set here, so that's not great. You can see our test accuracy is only 49% accurate, so not a great accuracy there. So what we're going to do now is we're going to start from the pre-trained parameters. So we just set this to true, or if you've got a newer version, you can use or define the actual weights of your model. So what I'm going to do is I'm going to change this name because we'll get a warning otherwise. And I'm going to run this whole notebook again and see how we go. So restart and run all, just make sure everything's refreshed. And we're just going to not freeze our model yet. We're just going to train the full model again, but starting at that pre-trained set of weights. All right, so we'll see what happens. All right, there you go. We can see that we now have an 88.2% validation accuracy. All right, it took 38-ish seconds to train. You can see while our training accuracy also converged to 100% this time, our validation accuracy is much higher, and our test accuracy now is 88%. So we've got a much higher accuracy simply by starting at those pre-trained parameters. So you can see why transfer learning is such a popular technique. We've got 38% more accurate simply by starting with these pre-trained weights. The STL10 dataset, like I said, is fairly similar to the ImageNet dataset that these models were trained on. So, it's a pretty, it's probably guaranteed to work in our favor. But even if your dataset is not exactly like ImageNet or contains maybe a very small subset of ImageNet, you still should see a relatively big improvement in the accuracy. Right. So what we'll do now is we're going to uncomment out just these 3 lines here. And what this is going to do is going to freeze the model parameters. So what it's going to do is going to freeze all of the model parameters, but then we're going to overwrite the final fully connected layer. So that final fully connected layer will have requires grad equal to true by default. And so that will be the only one with requires grad equals true because we've reinitialized it, and all the other ones will be false, so they won't actually train. So we'll set this to 3 and we'll go again. And we'll see how we go. Right, so training is over and you can see we've got a 70% validation accuracy. So it's not quite as high as before, which was 88% accurate, but you can see that we have trained in quite a bit less time. So it was 38 seconds-ish or 35 seconds-ish before. So over 10 seconds less training time. Again, this model isn't huge in comparison to how big they can get, and we only trained for 10 epochs. So, maybe not a huge amount of time saved, but you can see that we have saved some time in training if you were to scale this up to larger models. The reason why the accuracy isn't quite as good as before, you can see we haven't actually overfit as much, right? But the reason why potentially this accuracy is not as good, even though, as I said before, the STL10 dataset is very similar to the ImageNet dataset, so only changing that last linear layer should be, not too much of a problem, is that these models were pre-trained on ImageNet, but at an image size of about 224 by 224, and our images are 96 by 96. While convolutions can be scale invariant or are scale invariant, those initial layers of the model are probably expecting features that are quite a bit smaller, because ours are effectively, we're talking about per pixel, so how much information is contained in a pixel. For smaller images, it's more information than larger images, right? So those first few layers are probably expecting larger images, so they're looking for smaller features. So we need to update them potentially just a little bit to accommodate for our smaller images. If your images weren't too different to 224 by 224, then it might not be as big a problem, but ours are quite a bit smaller, less than half the size. What you could do is you could train the full model for a few epochs, then save, then freeze, and then only train the last linear layer, right, to prevent potentially overfitting. But the overfitting tends to happen quite quickly when you're training the full model. So let's have a look at some of the other models and see how we can use those as well. You'll notice that we've got another popular model type here called EfficientNet. So let's use an efficient net. You can see this efficient net B0 has only 5.3 million, so half as many parameters, but has a higher accuracy than the ResNet 18 that we're using. So let's use this efficient net B0 with these model parameters here. So let's use this one, pre-trained true. I think hopefully this will be the default values. Let me just double check. Okay, so we'll download those and we'll train from here. And we'll use efficient net, just change this name. Efficient net. Which one is it? B0. Efficient net B0. So let's have a look at just quickly have a look at, we'll leave ResNet name. The model architecture. So here when we've trained the actual changed the last layer of ResNet, not all of the classifiers have the same way they've defined the last layer. For example, this efficient net here, it's not called FC, it's actually a sequential block with dropout and linear. So we have to go into that sequential block and update it manually. So I'm going to reset this first, and I'll show you how we can do that. Okay, so I'm not going to freeze any layers. And I'm just going to comment this out for now. So what we're going to need to do is we're going to need to go into model. And we're going to, where are we? So it's called classifier. You'll see it is a sequential block, and we can index this like a list. So you can index the last one. You can see it is a linear model. And we're going to do a similar thing to before. In features is equal to features. And then we're going to overwrite this with our linear layer. Boom. So it's that easy. If you want to have a look, or if you want some code that does all of this for you, I do have another repo just called, if I have a look at my repos real quick, called Pytorch classifier. And in this module, or this script here, I do have an implementation that works for replacing that last layer for most of the different types of models. Right, in the next section as well for the classifier, I also have this inbuilt into the train class. So you can have a look at that if you want to look ahead. But for now, we'll just do it manually. So just be aware that certain classifiers have different ways they've created that last layer. All right. So this model says it only has 4 million parameters. Maybe I selected the wrong one. This is 5 million. Anyway, all right, let's train it and see how we go. So this should train a bit quicker, but I'll see you when it's done. All right, so training is done. You can see we've got an even higher validation accuracy now with our efficient net, 91.6, so very nice. You can still see we've got some overfitting. Again, the dataset is still quite small, and we've got a test accuracy of 91.05. So hopefully that has inspired you to train some of your own neural networks and see how you can use transfer learning on your problems. These days, transfer learning is again probably the first step that most people use if they want to train a classifier. You'll note that transfer learning is also used as a way to initialize other types of models, or you might use a classifier to not necessarily classify, but the features from the classifier. So we replaced that last linear layer, but what you can also do is chop it off or just remove it completely and use the features from those convolutional layers as an input to a different task, right? Your task doesn't need to be classification. Your task can be something else as well. You can put it in a whole nother network on the end of these pre-trained classifiers that does something completely different, right? It could upsample back to the image. It could, have any sort of outputs as well. You don't need to just replace the last linear layer. You could use this model as another module inside of a larger network. So how we've seen how we can create smaller modules and build up a larger network, you could also use one of these networks as a module on its own inside of another larger network. So there's a lot you can do and a lot that has been done with pre-trained models. And as you can see, right, it's pretty much, it's such a great improvement that you'd be crazy not to do it. So anytime a classifier is needed, you'd always use these pre-trained models. The only case where it might not help you much is if those pre-trained models, the data set they were trained on, is a lot different or quite a bit different from your particular data set. So like I said, this ImageNet data set here, you can have a look on the website for ImageNet and have a look. You can download the whole data set. It's quite large, but you can look at some of the images. The images are natural images like the STL10 data set as well. If your data is not like that, if you've got, images of X-rays or cell cultures, that might be a bit different or a completely different data type. It might not be pictures. It might be some other sort of 2D data. If it's very different than pre-training, might not help you at all. And what we're going to see in the next section is, what do you do in that case, right? It's not over for you if you can't use these pre-trained parameters and you don't have much data. There are other techniques, and we're going to see how we can leverage this 100,000 other 100,000 unlabeled images. We're going to see how we can leverage those in order to get a better model performance. But that's all for this video, and I hope I'll see you in the next one.